So I'm going to start with my NSF hat on, talking about two programs that are relevant to what we've been talking about today. We've heard a couple times mentioned the Cyber Physical Systems, or CPS program. Basically, this is a program that's been running, I think, for 7 or 8 years to develop network systems with sensors and actuators that interact with the physical world. The other program of interest is the National Robotics Initiative, which was established 5 years ago. In fact, it was established 5 years ago at Carnegie Mellon by Obama. And this is a multi-agency initiative to develop collaborative robotics, robots that interact, work with people, there's a lot of common interests between the CPS and the NRI communities. And so about a year ago, NSF instituted a workshop that was called Future Directions in Cyber Physical Systems, Robotics and Autonomy, in which the principal investigators from the CPS community and the NRI community got together with some of the leaders and some of the program managers in the various areas to talk about the future of CPS and NRI. And it started out as a discussion about, what was the future of CPS and NRI. Very quickly came down to talking about autonomy and the need for autonomy. And the drivers that were indicated were that these systems, both the CPS and robotic systems, more generally AI systems, are going to be put into very safety critical applications. And so the safety of these systems, the robustness of the systems are very important. The other drivers are that these are physical platforms that are operating in uncertain environments. And the uncertainty is something that we just can't get away from. As was pointed out a little earlier, there's a couple of reasons for this. Again, we don't consider laziness, but uncertainty is fundamental, and this is an issue that needs to be addressed. And then, as the last panel was talking about at length, guarantees of correctness is a big driver, especially in the CPS community. Less so in the robotics community, but we're coming at it more and more. So the challenges that the workshop came out with in their report were fourfold. The first one is safety, and then resilience, handling uncertainty, and learning and adaptation. One of the things I was a little worried about when noticing that I was almost the last speaker here was that the issues I wanted to talk about were already going to be talked about by other speakers, and in fact that happened. So in particular, a lot of what I'm going to be talking about Tom Dietrich talked about in the morning. Hopefully you've all forgotten his talk by now so that this will be fresh. But those of you who still remember, it'll be like, oh, all right, second data point here. So those are the challenges. And what I'd like to argue is that the last two challenges, resilience, handling uncertainty, learning adaptation, are all intricately associated with safety. And they aren't sufficient to lead to safe systems, but they are necessary. So I'm going to be talking about those and turning my hat over putting my CMU hat on and talking about some of the work that my students have done in the past and currently that relate to resilience, handling uncertainty, and learning and adaptation. Again, I wasn't sure when I put these slides together how much the other panelists would be talking about models. Fortunately, this has all been talked about, so I can go through this very quickly. But basically, the idea is that AI and autonomous systems, formal verification, all rely on models. And the bottom line is models are all approximations of the world. And so in order to deal with the real world, we have to be able to deal with approximate models. And my point is that the designers of the systems need to be aware of the limitations of the models. I think Mike made that point very eloquently in his talk. And in addition, the systems need to be aware of their own limitations, the limitations of their own models. And again, a number of speakers, in particular Tom, mentioned this very eloquently. So I will try and mention this less eloquently. Tom talked about the use of ensemble of models, and for me that is a key aspect of resilience. The idea is that, again, if you have a lot of if your models are approximations, you may not have a single model that works best for all situations that you find yourself in, and so instead you want to use the best model for the situation. So having an assembly of models, in our case we're using a hierarchy of models that are structured in certain ways, then we can reason about which model to use in which context, and then hopefully come up with a system that's more resilient because it's using the right model at the right time. So this is work currently being done by a PhD student in robotics, Breland Kane. It's in the domain of navigation. You have a number of different models. Some of the models are just geometric. Some of the models include dynamics. And the idea is that you start with the models that you're most confident in, that are the best for the context as you believe it to be, and then your experience will tell you, as you move through your environment, the experience will tell you what models you should be looking at, and so you can replan according to the best model available. And how you determine the best model available is you look at your various models, starting at the current model that you have. You go through this hierarchy, and you look for a model that explains any failure that you might have seen. Okay, so I'm driving I'm driving in Pittsburgh, and I'm using a relatively simple model of the vehicle-road interaction when it's dry, and then I'm driving along. All of a sudden, I hit an oil slick or black ice, and I realize that I'm not moving in the way that I thought I should be moving, and I start looking at what models can explain that. Well, I have a model about slip and vehicle-terrain interaction that I can reason about and say, well, that model would predict the failure that I'm seeing. It can explain the failure that I'm seeing, and therefore that might be a model that I could use. And so basically that's how this works. Here's a very simple case where the system starts off with a 2D model. It knows about projection of obstacles that are basically at its sensor height, but doesn't really know about these overhanging tables. It makes a plan that takes it basically through the table. It starts moving and encounters a failure when it hits its head against the table. You know, that's a shame, but it's not catastrophic, fortunately. So it backs off of that and then switches to a model that starts using the new information that it's gained, because it realizes that since it's hit its head, it's got to reason about the full 3D space. It starts planning to all the waypoint goals that is in the original model, finds a connection that is feasible in that higher level model to some waypoint, and then what it can do is it can execute, it creates a new plan that basically takes it from the failure point to that waypoint number 2 using the more sophisticated model, and then it can continue on with its lower model plan. So it's a fairly small patch to the plan, but it's able to get it through the failure case by dealing with, by using the model that's best associated with that context. So that's resilience. So next is handling uncertainty. And again, I think there's been a lot of mention about the need to explicitly handle reason about uncertainty in the models. Jeanette talked about the probabilistic guarantees of safety. I think this is very important. To me, this is much more realistic than trying to use these more abstract models to get definite guarantees, partly because, as Claire talked about early in the morning, these guarantees tend to have much wider safety regions than one would like in practice. And so the system given the probabilities, you can get a much tighter guarantee, I think. So this is work that was done. Mike Wagner was involved in this, doing a hybrid safety system where we have a human interacting in proximity with a robot in a manufacturing work cell, and we want to try and keep the human safe. And again, it's very difficult to guarantee 100% safety and still allow the person to get near the robot because who knows, a person could be Usain Bolt and he could be running through the work cell at whatever 5 meters a second, and if in order to make sure that he wouldn't hit the robot, we'd have to keep the average person very far away. So basically, we're using uncertainty in fusing our sensor information using evidence grid. We're using uncertainty by plotting a probability distribution of where the robot could be and where the person could be in the next time period. So where the person could be or where the robot could be between the current sensed information and the next sensed information that we might get. And by expanding the robot and expanding the person according to that model, we can detect the probability that there was an intersection between the person and the robot. And in those situations, we can stop the robot to avoid the potential for collision. Tested this a lot, both with mannequins and this is not working. Oh, here we go. There's no grabby thing. So unfortunately, you're going to have to sit through a little bit of dullness before you see the other dummy testing the robot. So Mike was not really happy with me doing that, but yeah, that wouldn't have helped much. But I do have all 10 fingers, so nothing serious happened.
What's the worst that could happen? You could be dead wrong, right?
Literally, yes. So the third issue that I want to talk about that this report mentioned was learning and adaptation. Again, Tom talked about the need for monitoring for monitoring during runtime and doing adaptation to the models. I think this is very, very important, again, because we're always going to start out with models that our approximations are inadequate. And what we're looking at in this case, this is work with JP Mendoza, who's co-advised with Manuela. What we're looking at is models that are subtly different in certain parts of the state space from our default model, from our baseline model. One example that we have here, here we go. One example we have here is a little soccer playing robot that doesn't know about that little bump in the field there, and it's trying to score into the hole. Sometimes it works even over the bump. Most of the times it doesn't. When it's not going over the bump, it scores much more with a much higher frequency. And the question is, can we learn a model that is more accurate given a relatively small amount of data? So unlike a lot of the machine learning algorithms that can look at Wikipedia or all the images that Google has, we're dealing with a relatively small amount of data, And as Drew pointed out, we're dealing with data that's in situ. What we're looking at here, so this is actually a simulation of that particular experiment, but we have here the probability that we succeed in a shot is 0.8, and in the anomalous region, the probability is 0.2. And I'm sure you can all see where the anomalous region is from here, but the system is is in fact able to pick that up. It is representing the anomalous region with ellipsoids, so it's not a completely accurate representation of the anomalous region, but it actually has fairly high precision recall for many situations. This was used in a real application for the robot soccer, in which it determined that one of its approaches, one of its plays, was succeeding actually less frequently than it thought it should. It used this mechanism to detect an area of the state space in which this anomaly occurred, was able to improve that model and improve the overall performance of the system by having this improved model. What's interesting is that the system had no idea why that happened. And the researchers looked at the model, looked at the code, went back and tried to analyze it, and actually came up with a semantic understanding of why that happened. So to me, this is the next step. We need to be able to look at these types of statistically generated models and come up with, from kind of our first principles understanding, come up with explanations, causal explanations that can explain that can be then used to generalize those situations to other similar situations where the same problems may occur. So just in conclusion, the idea is that models are very important in both autonomy and AI. All models are approximations. So what we want to do is have the system be self-aware of its own limitations, self-aware of the models that it's using, being able to use the right model, use those models correctly, improve the models when necessary, and through this idea of resilience, handling uncertainty, and learning adaptation, we can become closer and closer to the ideal of a safe AI system. Thank you.